So in this video, we're going to talk. In the last two videos, we talked about the Tresca yield criteria and the von Mises yield criteria. So what we're going to do now is we're going to look at, in the case of plane stress. So for plane stress, all of our stresses along the z-axis are going to be zero. So our shear stresses, our normal stresses along the z-axis will be zero, and we're just going to be looking at cases of biaxial stress, and we want to sort of define we're going to visually define the Tresca yield criteria and the von Mises yield criteria using graphically by plotting the first principal stress on the x-axis and then the second principal stress along the y-axis. All right. So if we look at the case where we have two positive principal stresses, so we have biaxial tension, and we draw the Mohr circle for that. What it ends up looking like is we have sigma p1 here, we have sigma p2, all right, and then our third principal stress is 0. So this would be 0 here. So we would have our 3D Mohr circle would look something like this. All right, and our maximum shear stress would be here. All right, and um, so um, so so our sigma p1 would have to be equal to our yield strength, and the value of sigma p2 really is irrelevant because it won't affect our tau max. So if we look at our graph here, we can draw on our x-axis the value of sigma p1 at our yield strength, and if sigma p2 is positive or greater than 0, it doesn't really matter if it's from this point here, or sorry, it doesn't really matter unless sigma p2 would also get to the yield strength point here. So we're going to just draw a vertical line that would represent case number 1. All right. So for case number 2 occurs when we have sigma p1 is in tension and sigma p2 is in compression. So in this case, we would have something that looks like this, where this would be our sigma p2, and then our sigma p1 would be here. All right, and then our third principal stress would be at 0. All right, so if we draw our Mohr circles, we end up getting this for our Mohr circle. So our maximum shear stress in this case, our tau max, would be equal to sigma p1 minus sigma p2 divided by 2. Okay, so if so what that ends up looking like is it looks like a a line that will go from the yield strength if you had only sigma p2 being applied to if you only had sigma p1 being applied. So it'll look like a line here would be the boundary between failure and no failure within the material. Okay, so so this would be equal to sy here. All right. So then the last one would be if you had two compressive stresses. All right, and in that case, if you have the two compressive stresses, what you end up getting is you have this could be sigma p1, and this would be sigma p2. So our 3D Mohr circle would look something like this, where our tau max would be equal to the absolute value of sigma p2 over 2. All right, so which is going to be equal to which is going to be equal to the yield strength over 2. All right, so what this ends up being is going to look very much like sigma p1, or the case 1, is it'll just be a horizontal line drawn at the negative yield strength here. Okay, so this half of the envelope is for cases 1, 2, and 3, and then the last cases are 4, 5, and 6. So 4, 5, and 6. Question number 4, or number 4 is going to look exactly like case 1. The only thing is like the sigma P2 is going to be switched with sigma P1. Alright, and then we can do the same thing for number 5 is going to look a lot like case number 2, and then number 6 is going to look a lot like case number 3. Alright, so what this ends up looking like is it ends up looking like another half of our envelope here, where this point here is SY minus and minus SY, and then the top part of our graph here is going to be, this is referring to case number 4, this part here is referring to case number 5, and this last part here is referring to case number 6. Okay, so what you could do with a graph like this, or the purpose of a graph like this, is if you had a case of plane stress and you knew the principal stresses sigma P1 and sigma P2, you could plot them anywhere on this graph. So if you had a case where you knew sigma P1 and you had sigma P2, you could plot them as a point on X and Y. So let's say you had one point here, a case of stress where this was your point. Since it's within the envelope, you have, if you're within the envelope, you have no failure. But if you're outside the envelope, like if you were in this case, if you had a point outside the envelope, alright, you would have failure. Right? So it's a very simple tool you could make for any material, is that you could make a graph like this, and then once you calculated sigma P1 and sigma P2, you can look it up and on the graph, and you can see visually whether or not you're going to have failure occur or not. Right? So we can do a similar process for the von Mises stress. So if we have a case of plane stress, for the von Mises, we can plug in that sigma P3 would be 0 in the case of plane stress. So if we plug it into our von Mises yield criteria, we know that the yield strength would be equal to our von Mises strength at the yield point. So if we plug in sigma P3 is equal to 0, we'd end up getting the simplified equation for our von Mises stress. Alright, so if we use this equation, we can create another plot just like we did for the Tresca yield criteria. So we have intercepts where in the cases of uniaxial tension or compression, where these will be our yield strength points. Alright, and if we draw this all out, what we end up getting is we end up getting an elliptical envelope here. Alright, so if you're outside the envelope, failure will occur. Alright, if you're inside the envelope, you're safe from failure. Alright, and then the last part is you have Tresca, comparing the two cases. So if we draw our von Mises case again, alright, we'll have our ellipse about the intersect about the yield strength points. Alright, alright, and then for the Tresca criteria, it'll look something like this. Okay, so what you'll notice is that the Tresca criteria is always going to be within the von Mises criteria. All right, so and what you'll notice is that the the Tresca criteria is always more conservative than the von Mises criteria, and then there are 6 points where the two theories do intersect. Typically, designers will use the Tresca criteria if they're trying to be more conservative. Um, it's also a little bit easier to apply than the von Mises case. But von Mises has been shown to be experimentally more accurate, so it seems to this theory agrees more with experimental results of different types of loading cases. So if you're trying to be the most accurate, you should probably use the von Mises criteria.